So yeah, you got like 5281 negative 7, sure. And with all this, you store a pointer to the first element. And then if you want to access any of the other ones, the way you do it is you just access pointer plus, let's say, 3, and then you dereference it just like you'd have to dereference this pointer to get to 5. So this pointer plus 3 would get you 0, 1, 2, 3. So that element. And that's how you get access to it. So you don't have to know what's in either of these 3. Like, you never have to touch it. You just do add 3 to this address, and at that address, there's a third value in this pointer. So that's very quick, very efficient that way. That's how arrays work. However, as you guys experienced, if you want to make this array bigger, like let's say now we try to add like negative 100 or 13, like if we try to add that on, this array isn't big enough. So we have to go through the whole process of making a bigger array, more elements, copy all the data over, and then we can start adding the new elements. So with arrays, since they have that allocated size, if you want to get more of it, then you're stuck. Also with this right here, I think if I did my errors correctly, then you have these 2 blocks of space that are allocated, but you're not actually using them at all. So like this is just useless information that is wasted because nothing's being stored there. But it's there so you're more efficient to like increase or decrease this. Well, I guess in this case, it's definitely just increase the size. So you could still add 2 more, but it's allocated space that you're not using. Linked lists fix this problem. They also make it so you don't need continuous chunks of memory. So the way a standard linked list works, I can just clear all of it, is that you still use pointers because since it's unknown allocations amounts, we still use the heap. Just now, our pointer is to something called a node. And that node is just a single thing. It's got a number in it. So in this case, I'm saying 1, sure. And this node is all by itself. It also comes with some other information. So think about it as some sort of class. So in this case, it'd probably be a struct just because conventions. It would have the data that's stored inside of it, and then a pointer to another node. So by itself, it might just be null pointer. So like you didn't have any other information, but if you started adding information, you would allocate a new node of memory, store the information, and then set this pointer instead of to not be pointing to null anymore, but to the new node. And then this node would be null. And so if you kept doing that, this information can be anywhere. Since we're using pointers, it does not have to be adjacent to each other. And you only allocate as many as you need. So there's no running out of space with linked lists because you just allocate another node. And it could be anywhere, so it's not limited to adjacency. And there's no wasted space. The issue now is, let's say I wanted to go to this element. Let's change color, getting a lot of light blue. We want to go to that color. We can't just do pointer plus 3 dereference anymore because pointer plus 3 would be along like a chain of continuous memory here, 3. But we're not using continuous memory. So what we have to do, I'll fix that. What we have to do now is instead go to, so we have to dereference pointer. And then we got to do dot, and this might, in the arrow in your data structure might be called next. So it'd be next. And then, so we started here and now we're here. And then we got to do dot next. So now we're here and dot next. Obviously, this seems a little wacky. Like you wouldn't really want to do this. But actually, it wouldn't be dots. I'm just going to get rid of that. You would use the member associated thing. So it'd be like that. Because those should all be pointers. Yeah. Okay. So you'd say pointer next. So pointer's this, and then next, next, next. And so now we're there, and then we dereference that. I know this is a lot, but the whole point is you have to go, the goal I'm trying to say here is you have to go through each element to get to somewhere in the middle. Because the only way to get access to those is by following the chain of the linked list. So this is not very useful for getting information in the middle, but it's very storage efficient. This also, it's really easy. Oh. Is a node considered a pointer then? So the node itself is memory allocated on the heap. So a node itself isn't a pointer. However, each node stores a pointer to another node. So pointers are just memory addresses, right? So each node stores a memory address to where the next node is located. Does that make sense? But just like if you had an int pointer, the integer itself is not a pointer, but you're storing the memory address to where an integer is. And so that's the same thing here. So yeah, each of these stores a node pointer, and that says where the next one is in memory. Technically, okay, so my syntax is about to get fucking wild. But, and I'm only gonna go to, I know I probably erased way too much. I'm gonna try to go to this one. But so what we'd wanna do, if you wanted to use the dot operator instead, it'd be dereference pointer. So pointer is like this arrow, so dereferencing, we're here. And then we'd want to do dot next. So now dot next is that arrow, it's that address. Dot next is where 2 is located. And then, oh my God. Here we go. And then you need to dereference that. So now we're here. Start in there. There we go. And then dot next. I said I wasn't going to go this far, but we'll go one more. And then dereference that. And so now we're there. So the arrow operator is a very, like we talked about before. If you had an int pointer ptr equals new int, you could, no, it's for classes. So if we had like a string pointer. To do like pointer dot, I think length or size for strings, whatever strings have for length measurement. This is a string pointer, so you can't just use dot, you have to use the arrow, and the arrow is shorthand for dereference dot. So, or just remember, so the arrow makes that way more efficient. So when you're doing arrow, don't forget that that's the shorthand for dot next. So the nodes themselves exist somewhere. You're just storing an address to them. And so you go to the address, dereference, and then go to the next one. I say that just because a lot of people get confused by that, me and myself included, when I first did a linked list project. So just understand the information you're accessing. Is it a memory address? Is it an actual node? Which one are you dealing with at that moment? Okay. So went on a little tangent there. I think what I was about to say, I'm just gonna erase, I'm gonna clear it. So like, let's say we had just a little, and we started here, sure. And then this goes to null. So if we wanted to insert an element, if you had an array, we had like 1, 2, 3, 4, and you wanted to insert 5 right there, you would have to first move every element down that was after, and then you could put 5. So that's really inefficient. But with here, you just do the whole thing that we did. So you start with pointer, go here, and then once you're here, you say, okay, first make a new node, store whatever the new value is that you want to store. In this case, we said 5, sure. And then make this, because this initially would probably start with null pointer, just by default, like a default constructor for a node. And then you'd say that pointer, reassign it to this pointer, because remember, I draw them as an arrow, but really it's just a memory address. So it's saying, have your pointer point to this memory address. It's not like a vector where I'm saying, copy this vector. So now that you've got that, then you'd say, make this pointer point to here instead. And so now we very easily added this new node in there. The only things we had to change were the stuff that I said in green, and even then we only changed one thing, everything else in green. The only we changed was this in orange. Everything else was just added. So nothing else had to be affected to add this. So linked lists are really good for adding information inside the middle. So all that's really just to give you context. So like show you how linked list functions, and then give you context for why linked lists are useful. Any questions about like the usefulness of linked lists or like a use case? Awesome. Hold on, give me a second. Okay, so awesome. Now let's actually go through some of this documentation. Share screen. Okay. So some background. We talked about how memory worked. So this is in the stack how memory would work. So you got X, Y, Z ints allocated. You allocated a car, and then a character RGBA, and then a pointer. So this is stack memory. Normally when not normally, but so this is creating a car on the stack, and then the pointer stores the car's address in memory, so it's a stack pointer. It could be, if it was not, if it was vehicle star car equals new car, or I guess this would be star pointer. It would look a little different because you use node stuff mostly on the heap. You wouldn't really do it on the stack. You could, you definitely could, but that would kind of defeat the purpose. I guess it wouldn't. Yeah, no, you could definitely do it on the stack. So yeah, more stack talking about memory. So here's, we talked about arrays where it's like a continuous block of memory. Here's where if we wanted to say like add a new element, we couldn't do that because it's a continuous block of memory. So we'd have to make a new array and like literally this is what we talked about. I did not know this was here. Not gonna lie. So yeah, make a new one, copy it over, and then deallocate that old array. So that also, this is showing that now there's this new available memory, but this new available memory isn't large. So like it fucks up memory, like there's now just some random addresses in the middle that can be used, and that's a little bit weird. And so here's the linked list. So this is a more linear approach because a memory address is just like a line of addresses. There's not like two-dimensional memory addresses. But you can see how it's like jumping around, like it, because you can, wherever there's space for a node, it can get allocated there. So as long as there's a space for a single node of memory, it can be allocated wherever. So these pointers are just pointing to where the new address is, and they have no idea where it is. Like second has no idea where fourth is in this case. Like there is no connection between them at all. Second, in this case, only knows where third is. And as long as you got that, it doesn't care where everything else is. So this is the same like with people. If you were ever in like kindergarten and your teacher said, keep track of your buddy, and everyone had like a unique buddy, so it was like a long line of buddies, you would just keep track of the next person. And as long as everyone kept track of their next person, everyone was kept track of, as long as there wasn't some random person floating in space that no one was keeping track of. And so maybe like the teacher keeps track of the first one. And the last person doesn't keep track of anyone. You can actually technically have, I don't know what the term for it specifically is, but you could have a linked list that wraps around on itself. That's totally legal. So instead of having the last one point to null pointer, it just wraps around. So that's super fun. We talked about the advantages and disadvantages. So yeah, removing information, also super efficient. So with an array, if you wanted to remove an piece of information, you'd either have to shift everything down or you'd have an empty block. Both of those, one of them is computationally take extra time if you have like a really long array. The other one would be bad to just leave a random memory in your thing just empty. But here, you just move the pointer. If you wanted to remove an element, you just move the pointer to the next one. And then same thing with adding a new one. So we talked about node. We talked about linked lists. We didn't talk about single or doubly linked. So it goes into more detail there, but what we've been working with is singly linked. So you have your initial pointer. I should really just... So if we have a pointer and then some memory, and like I said, I'm doing it linear now just for simplicity in my drawing, but it doesn't have to be like conceptually, you don't have to think about it that way. You could have like something back here and it points back, but that takes more drawing time. So this is a singularly linked list. What you're going to be implementing is actually called a doubly linked list. And instead of a single pointer, you have two called head and tail. And so now every pointer knows where the next one is and they know where the previous one is. This really just makes a lot of computations like inserting and deleting. You can choose if you do it from the head or the tail, because like here, in this top case, if you wanted to add something down here, you would have to go through each element, then make a new one, reassign the pointer, and then that's to null. If you wanted to add one in the head, then you just make a new node, set the pointer to here, and then set this pointer here and get rid of that. So then it'd be following along that. So it's much easier to add to an end if you have a pointer to it. And so that concept transferred to here. So now if you wanted to add to the head, you would just do new pointer, point to there. This, what you do have to make sure that the previous one points to there, and now head points to there. Crop that out. I guess it'd be erased. There you go. And so you could do that for both ends very easily. So that's a double versus singly linked list. So yeah, head, tail, that's in like a doubly linked list. Technically, a lot of singly linked lists, they have a head as well. So instead of just using pointer, they say head. But doubly linked lists have a head and a tail. So now we're getting into the actual implementation. So any questions about like how linked lists work? So that's all, like, you don't have to know how to implement one yet. We're about to start covering that stuff. Okay. so now looking at some actual code and implementation. First thing is that node class. So in this case, we did, oh, that's mine. Stop it. So here, it's talking about an integer linked list. So all of this is all just linked a list for, oh wait, what's happening here? This isn't even for a linked list, is it? No, this isn't a linked list. This is just talking about a nested class. Okay, so this right here isn't even a linked list, but it's talking just about a nested class. So if you know that the class you're about to make, or your structure in this case is what it's called here, is only going to be associated with some other class. So in our case, if we have nodes, you should be making a unique node structure for your linked list. And there should never be like an individual node. It should always be associated with a linked list. You can make a nested class. And so now in here, it's just relational stuff. Like honestly, when I make a linked list, I don't do a nested class. But it's saying when you do it like that, when you have to make a nested class, if you're not inside of my class, then you have to say like my class colon nest. Oh, right here. So like right here. This is about template classes. It's not, oh, I don't like this explicit here. Why don't I just start writing my own? Excuse me. Okay, so hashtag include pragma once. Hashtag pragma once. I'm an idiot. And then Steam, class Steam. So then in here, I'm just gonna put it in public to make it more sick. There we do struct, and remember structs and classes are basically the same thing, except structs default to public while classes default to private, like the member variables and stuff. So structs are good for any information that you do want to just have all the information be public, which nodes you do. You want to have easy access to all the information. So struct node, and so now int a, there we go. Now in here, we did, to get access to make a node ourselves, we'd have to do steam : node. There. I'm going to close that. So here, if we wanted to make a node, now it's the node associated with Steam. And so this is nice, just so that anyone who makes their own node class, it's unique. So you don't have to make it, like you don't have to make a super specific node in order to not mess up anyone else's. It is specifically the node associated with my Steam class here. Now, if you're inside of here, like if you got a function in here, you don't have to do that. You just do node. So that's a lot more straightforward. But in here, don't have to do that. Okay. So yeah, it's just so when you're outside of your class, it makes it so your node is unique to any other person who implemented a node. Oh, and there's the lights. Okay. Okay, so here's a nested node class relative to a linked list. Doesn't have to be called nested node. We call it whatever you want. This is just to show you that's a nested node class. Oh yeah, benefits versus drawbacks of arrays linked list. So yeah, arrays, super fast access because you don't need to go through each element to find the next one. You just add a number to the pointer, and that's how memory addresses. You go forward, and you go to that memory address and get the information. So fast access, and you can also get randomly fast, like it's any, that's true for all elements. Arrays are just really good at accessing, changing, and anything to do with changing an array, because they have to be a single block of memory. That's the bad thing here. linked lists are very good at changing memory. So memory fragmentation, that's talking about like, if you wanted to allocate a billion size array, you would basically have to put it at the very beginning of your stack, even if there's random little bits in memory elsewhere, because arrays have to be a continuous block of memory. Linked lists, you wanted to size billion, you could fit it into any little crevice in your memory allocation, which happens, that's why the heap exists, so that you can have weird crevices. A stack is the thing that you couldn't do that. So have weird little crevices. And so linked list is very good at what's called memory fragmentation. So that was talked about like here. So this is fragmented memory. Linked lists are very good at that because they can be wherever. But then they are bad at that random access concept, because you have to, in order to go to the fifth element, if you're starting at the beginning, you'd have to go first element, second element, third, fourth, fifth. Like you have to go through all of that. And then there's usually extra memory overhead to store the information and the memory addresses you need. Okay. So that's just generally how to implement linked lists versus arrays. Now for the one you're doing, you guys are implementing, the final thing you will be implementing is basically a linked list with every sort of possible function anyone could ever want. Like when I've implemented linked lists myself, they're usually much more simplistic than this. I don't need all this stuff. We have you do a print forward, a recursive print forward. Maybe there's some like easier, like it's faster or something. You can test that. You have const and you have non-const versions of the same function. Like there's just any function that we could possibly want in a linked list, you guys get to implement. Luckily for you, it's broken down pretty nice. So if we go to Zybooks, this thing right here is the final result, but in Zybooks, you will be doing, do you guys not have linked lists yet? Where's linked list? Oh, I guess you can't see it yet. I'll talk to him about that. The linked list, the first one, you only have to implement a couple of the functions. And so it's a lot more simplistic. But then the next part two, so you can use the same code as before, but now you got to implement more functions. And more. And this, everything comes together. So it just kind of gets more progressively harder and harder. So you'll be using templates again. Templates. Nested classes make it easy to deal with templates because you just use the same template as the class itself. Ooh, yes. So when you're writing a nested function, if you're writing a function that has like a nested return type, and then you're defining it outside the class definition, things can start looking a little weird. So I guess this is where we're starting. So yeah, you got the return type, you're saying foo_t some function, because this looks like what you'd normally do. So nested though, so if you're outside the class definition, you do the class : nested class. So you have to do that. But it's also a templated function, so you have to add the little t here, just like you have the little t here. And then finally, you have to add a type name beforehand. So it's a lot of extra overhead to write class definition, function definitions outside of the class, but it's still good practice to get into. And then I guess here's some tips and sample output. Let's go through them and look at the tips. So yeah, start small, one function at a time. That's why we have it in different parts. So get out your IDE, start testing like with your own stuff, maybe copy over main and only run certain parts of the code, but like test each of these little things bit by bit. So yeah, outputting super straightforward. You're gonna need the big three once you start using them. Definitely. Oh, and the big three are wacky for this because here. So there it is. With an array, if you did new int clear, if you did int pointer ptr equals new int 10, if you did that, to get to allocate pointer, you just use delete with brackets pointer. With a linked list, if you got a linked list, and then variable name, some var. Inside of it, there is some pointer. There is a node pointer. And that does point to a singular node. It's just a singular, so at some point that was equal to new node. So, but it's a singular node, not an array of nodes. When var goes out of scope, you can't just delete pointer. You can't just do that, because if our whole array looked like, if our whole linked list looked like that, deleting pointer would deallocate what it's pointing to, but then all this other stuff is memory that is bad. So you need to create probably maybe 1 or 2 extra pointers. And so 1 to point to here, 1 to point to here, and you delete, so like let's say this is 1 and this is 2. You delete 1, and then say 1 equals 2, and then 2 equals 2 dot next, or dash next, and then delete 1 again, and then 1 equals 2, 2 equals 2 dot next, delete 1, 1 equals 2, 2 equals 2 dot next, and that's null at that point, and then delete 1. And then once 2 equals null, you don't delete null pointer. So that's something that you need to stop, figure out your end conditions there. But you have to go through each and delete each. So that would happen in your destructor kind of thing. Or if you were someone deleted a node, you have to delete the individual nodes. So you can't just delete pointer. So that gets a little wacky, definitely. For back to the recommended chapter in your textbook lecture videos for dynamic memory allocation. So yeah, you got to get real comfortable with dynamic memory allocation. I know for me, I really struggled for it. And I would like to say that the reason why I don't anymore is I truly understand that pointers are just memory addresses. Like that just is really ingrained to me. Obviously, there's probably some extra stuff in there. Like I've been doing this for a while. If it took me this long, there's extra information along with that I can't really verbalize. But it's the pointers are just memory addresses. And so when you're moving them around, understand that. Like that's the big important part for me. If I start seeing people like question, like if you have your code and say it doesn't work, probably the first thing I'm going to do with you is not change your code or tell you what's wrong, but just go through your code and say like, okay, your constructor, it has a pointer, it starts it with null. Okay, when you insert, you create a new node, you set pointer to here, and then you set next to null, that's great. And then when you make a new one, you set next to that pointer and then you're done. And so just erase that. So then if that's all your code does, and I would stop here and I'm like, okay, what's wrong? And then you say, oh, I didn't set pointer to equal to this new one here. So like you can see what you didn't do. Linked lists are great for visualizing and just understanding how those pointers move around and to point to different things, saying that they're pointing to new memory. So drawing it out is also super valid. Like you should easily be able to do this. I do this a lot with this project in office hours. You'll definitely, if you come to me, you'll almost guaranteed have to draw something out. Not always true, but probably. But yeah, I really love going through code. Like if your code isn't working and you think it should, go through line by line what your code's gonna do. Not end. Okay, and there's just some sample output. Okay, so last thing I'm gonna go through for the lab is just like a simple linked list overview, but any questions about like any of the topics in here? I'm gonna do an actual implementation so you can see some stuff. I won't do all the functions obviously, but cool. Okay, so in here, this is called steam.h, but I'm gonna rename it linked list. Got this node structure here. I'm just gonna do a singly linked list because I'm a baby. What do I want private? So I'm gonna have a node pointer head, and then maybe a node count, int node count. Sure. That's fine. Awesome. Okay. So here we got our default constructor. And this isn't even templated, so I'm not even gonna deal with that. And I'm gonna do void insert node. That seems good enough. So in here, default constructor, you just allocate what the default thing should be. I'm gonna say head equals null pointer. And node count equals 0. Great default values for both of those. And then in here, insert node, and it has a parameter. And data, sure. I'm gonna say node pointer temp. Oh, and then in my node itself, it means integer value I said, and then a node pointer next. There we go. So node pointer temp dot a, and it's arrow, not dot, but my IDE does that for me automatically, equals data. Insert node, I'm gonna say head. And I say temp, what do I want for, I want to say temp next equals head. Yeah, temp next equals head. And then head equals head equals temp. Yeah, that's what I want. So like I said, love drawing this kind of thing out. Is there like a nice blank? There we go, perfect. So what we got going on here is just annotate. So head starts at head starts pointing to null, and then I say temp points to temp is a new node, so it starts as just a node with nothing. So pointing, it's not even pointing to anything yet, really. I could probably make a default constructor in temp if I wanted to. That probably wouldn't be a terrible idea in the node, yeah, for node constructor. So that would probably be not bad, but I didn't do that. But here I allocated A and next, so that's fine. So A equals data, so whatever data is, and then temp next equals head. In this case, pointing to null, that's fine. And then head equals temp. So far, so good. If this ran again, so this goes out of scope. If this ran again, I'm going to say temp point is a node pointer, data, temp next equals head, and then head equals temp. So it's all looking good. And those are usually the two cases you really have to check. It's important to check when yours is going to be a doubly linked list. So you have head and tail. I'll go over a tail implementation in a second. But when both of them are pointing to null, so when nothing's been initialized yet, and then when at least one has been initialized, those are two usually important states to check. And it's more important, you'll see when we get a tail pointer, because there'll be a condition in there. Okay, cool, good. So that works. I guess we can also run it. We can make a void print function. And so we do current equals head. And I'm doing this because I'm about to like print out each thing, but as I'm going through each element, you never want to move head. So you don't want to say head equals head.next. Like you almost never want to do that, because moving head around, you should only be doing that when you're changing the linked list itself, not when you're trying to do so. So here I'm making what's called an iterator. And then I'll say like while current does not equal null pointer. And I think it's gonna it's saying there might, no, okay, that's fine then. Cout current dot a. So with that, make sure that I get ooh, I could also use a for loop and show you an error that I made. I know I made an error and I'm trying to find a good place to show it. So yeah, I'm gonna do for int I equals 0, I is less than node count plus I. There. Oh, I made another error as well. So yeah, this is going to be fun error fill time. Okay. So for this, I'll create a linked list. And I'm going to call it list, sure. List dot insert node head 1. I'm just going to call this multiple times. List.print. Okay, so with all that, what? Oh, I'm an idiot. Yeah. Okay, so I needed to do that. So doing that is saying in our little thing here. Oh, it's right there. So that was my B. That one isn't even an error that I saw. But I was just saying temp and then not even pointing at anything. So doing temp equals new node is what actually points it to a new node that exists in space. Might be on that. Mouse. Try running it again. So nothing printed out. And you're like, what the hell? Why didn't anything print out? Well, if we put a breakpoint here and then run the debugger, we hit the breakpoint. And if we go next, there, it just skipped over and you're like, what the fuck? Well, go to this. We see that node count is still 0. I never changed that. So just going into here, seeing what these values are, that's super helpful. So node equals 0, like why is it 0? Well, never changed it. And so up here, you can just go node count plus plus. And so if we stop it, move the breakpoint, try running it again. Now it keeps printing out 5, and you're like, well, what the hell here? This is where I'm showing off the drawing. You might already see it. Sorry if you do. There's only 2 of you, so that's really sorry if you don't see it. It's really sorry if you see it, because then I'm just wasting all of our time, but that's fine. It's good to go over it. So if our linked list was head, node, 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 share. So right here, we're saying node current equals head. So say current equals head. And then we see out current A. So we see out the information here. Let's change it to orange. Get the information here. Well, it's going through this loop, I is less than node count. And so it keeps just printing out this information. We never changed current in here. So we want to make current point to here, which in this case is equivalent to current equals current next. So that's what we need to add. It never switched places. Current equals current. What the hell is that? There we go. And so now as it goes through each of these things, it's going to print out and then move and then print out and then move. So clear all. Run it. There we go. That looks good now. Perfect. So that's a singly linked list. Stop. Doubly linked list looks almost the exact same, except now we add a node pointer tail. And then our structure needs a node pointer previous. And then here we do tail equals null pointer. So just adding that tail and then previous pointers is what you need. So then here we have to take into account sometimes if head and tail are both null, the first time we add a node, we're gonna want to end up with this. So tail and head both get changed. The next time we add a node, we just need to change the head node, so not tail. But if it's our first node that we're adding, you need to move tail as well, because you don't want to, if you don't move tail and just keep it to null pointer, then it's not doing its job. You couldn't add to head a bunch of times and then print in reverse. You should be able to do that. So the little check, we still want it. This is all good right here. Since if we're adding node at the head, then we know that the new node dot previous, we just want to equal null pointer. Like that's straightforward. Because if it's going on the head, then the other way. And we just need the previous to be null. So setting up temp. And then now if tail is equal to null pointer, tail equals temp. So head equal temp is a constant, but just this one little extra condition to make that work. Yes, that. Yes. Tail next equals head. Yes, okay. So then here, now we can have a print forward and a print reverse. So and then instead of head, it's equal to tail. And then instead of done next, it's previous. So you can basically just copy and paste that code. It's very nice. That should be how it works. Obviously, if you have a little weirder of an implementation, no judgment, but hopefully it's nice. And let's just add a little. There. Oh, yeah, cool. We're good. Okay, with that, I think everything's good. Might be wrong. We're about to find out. Oh, what happened? Exception thrown. Current was null pointer. Ooh. Why was current null pointer? So that means tail was null pointer, but we already printed out one. I did something wrong. Let's go find it out. Actively debugging. Okay. So that means there's something wrong with my something wrong setting up my previous pointer. So if we write this out, so first condition, we got head, tail, both those set to null. So I'm gonna say let's add 3 elements. That should show us everything we need. So we have temp, node, new node, data, next equals head, so that's a null pointer, previous equals null pointer explicitly. If tail equals null pointer, tail equals temp, tail equals null pointer, so tail equals temp. And then we always set head equal to temp. And node count plus plus, and then this is over. Okay, so that looks good. And that makes sense because in our, here, let's run it again, because it does print out, we go to our console, it prints out 1. So honestly, that makes sense that the first data we got worked because we printed out that information. But our issue will be probably in adding the second one. So here we go. So now here, we say temp equals a new node, data, temp next equals head. So that's fine. Oh, I see what I did. Yep, okay. Temp equals head. And then temp previous equals null pointer. If tail equals null pointer, tail's not null pointer, and then head equals temp. I think I made literally the exact same mistake that I told you about, or maybe even similar to what I told you about. So right here, the issue, right there. This was not on purpose, I swear. So right there, this head's next node was never properly pushed, like assigned to be the back one. So with this setup right here, you might be like, okay, we just need to say tails previous equals head. So let's do that. So that's an else here because the first one works fine. So tails there. But here we'll say tail dot previous, or tail, why is it not? There we go. Equals, in this case, temp. This is wrong. If you see that it's wrong, it's fine. I'm telling you it's wrong, so if you see why it's wrong, you'll figure it out in a second. But if we have this, like, okay, that should work now. That fixes our issue. We say like, ooh, this now points there. In that moment, it fixes our issue. So we run this. Crap, what? And we go here, and we're like 1, 5. Well, that's wrong. Why did it go to 5 right there? Okay, back to the drawing board. Literally. Okay, so for simplicity's sake, I'm not going to write out everything again. I'm going to go back to where we stopped before. So this was null. So now with everything we did, going back to this line, we say that. So this is the setup we have. And then that's after adding the first element. Obviously, we needed to do one more step. So let's add a third one. So temp. I'm just going to put it here, and I'm actually going to do a different color to make it a little more obvious because I'm about to draw over shit and stuff. Data equals A. Oh. There we go. Data head temp next equals head. That's fine. Temp previous equals null pointer. Oh, it's about to get whack. So sorry. And then if tail equals null pointer, tail equals temp. Nope. Else tail previous equals temp. So that's tail previous equals temp. Well, that's not good. That's not what we wanted. We wanted, what did we want? We wanted at this point in time, we wanted heads previous to be equal to temp. Yes, because at this point in time, we have not set head equal to temp yet. So with our previous setup, head would have been here when we were in this exact situation. So yes, this works out. We don't want tail previous to equal to temp, but in our previous case, head and tail were the same thing before we moved head. So that's why it looked like maybe we could have done tail previous, but no, we want head previous before we reassign head equal to temp. Oh, no, I did the wrong one. Previous. Head previous equal to temp. So there, if I undo some drawings. So in this case, with head previous equal to temp, now is that. Head previous equal to that. Awesome. And then a new color just because I hate everything. Head equals that. So I know this looks wonky. I'm sorry I didn't allocate my space properly. That's totally on me. But this is good now. So we've got tails pointer, left, right is correct. That middle pointer, previous to tail, the next previous data is correct. Previous to that, now the new head pointer has a data, next previous is right. That looks good. So adding a third element also might be helpful in some cases. Usually it's just those first two, but in this case it was the three. So drawing out the first three is probably a good idea then. And so if we run this, that looks clean, no errors. So moving around those pointers can be a little confusing sometimes, but the goal being we can draw it out together to see where an error occurs in that kind of case. Like it's not some magical, mystical woo data structure. It does just exist. They are just pieces of information, and we can like mess around with it like that. Okay, with that, that's kind of really all I wanted to show you. If you guys don't have any questions, that's it for this week. Like I said, this week is just this linked list. Make sure you get started on it. If you have any questions while you're working, please DM me, come to anyone's office hours. Either one works. Have a great rest of your day, Alyssa. My pleasure. You guys are welcome. And now it's just me. Ugh.